Okay, so this is objective 2. We are going to classify numbers in the real number system. Any questions on that? Okay. All right, so we're first going to start. You should have a paper that looks like a family tree, and I'm going to tell you a little story. Hopefully, it'll make sense and you'll be able to remember it. So, once upon a time, there was an old lady, and her name was Grandma Real. So, we're going to talk about everybody that's under Grandma Real, okay, that's in Grandma Real's family. Anybody have like a staple in your family that your grandma, your grandpa, they're the head of it, and, you know, everybody is underneath it is a part of that family? Anybody got families like that? Yes, you got some? Okay. If not, you know what I'm talking about, right? Okay. So, Grandma Real is going to go at the top. First name Real, last name Numbers. Grandma Real had 2 kids. Anybody know what their names were? 2 families that go under the real number system. I'll give you a hint. One is rational, and the other would be irrational. Have y'all heard of those before? How many have heard of them, but you don't remember? Okay. So we first have rational numbers. What do you notice about this family before we fill it in comparison to this family? This one has more circles. It's bigger. Okay. This is my one chance to pick on my older sister. So we're going to compare. This family's going to be like my sister's family. Okay. Those of you who went to Stewart Elementary and know my sister, what do you know about her family? She's got a lot of kids. Okay. Her husband had 2. She had 1 with her first marriage, and then they got married, and together they had 3. And so they have 6 children, okay? And it's a lot of kids. At one point, she had 4 kids under the age of 5. She had a 5-year-old, a 3-year-old, a 2-year-old, and a newborn. Can you imagine that? That was a lot of kids back in the day. Anyway, and I'll tell you, they're all different. They all look different, okay? They have similarities. They do, but they look different. For example, my nephew Wesley, he's dark hair, kind of olive skin tone, dark eyes. And then you go to my niece Caroline, and she's blonde hair, blue eyes, fair skin, freckles. And then you go to my niece Sadie, and she's got dark curly hair and big blue eyes. And they all look, you have, how many have siblings that y'all really don't look alike? You know what I'm talking about? That's not true. But you with me? Some families, I don't know if the genes are really strong and they all look alike. And then some families, they have similarities, but they don't. Each one looks their own. Yes? You understand what I'm saying? I know it's a far-fetched analogy. Stick with me. You'll get it. I promise. So this family is large, and they have a similarity. They have something in common, but they all look different. This family over here, which is going to be Irrational's family, is like my family. And it's very small. Do you know what my kids look like? I've shown you pictures. It's easy to tell which ones they are. They're redheaded, freckled, and fair-skinned. I bet if I were to have another child, I guarantee you, I don't know, but I guarantee you, I bet they would be redheaded, freckled, and fair-skinned. I'm in one of those families that my kids, they look. My son Reed, he looks just like my husband. I mean, identical. They're like mini-me's of each other. So how many are in this type of family where you look just like your siblings? You with me? So some families are like that. So we have Rational's family and we got Irrational's family. Now, here's the thing. What is the common denominator of this rational family? Okay? And here it is. It's the fact that you can take it and write it as a fraction. That's the definition of rational. Any number that you can take and write as a fraction is a rational number. Okay? And you may need to fill that in up in your box. Okay? Just fill in a box. So let's talk about that. I'm going to go ahead, I'm going to pop up the irrational definition, and we'll get to that in a minute. Irrational's family, They look all alike, and they are non-repeating, non-terminating decimals. And that's what they look like. Every single one of them looks like a non-repeating, non-terminating decimal. So let's come back to rational. I want you to tell me, think of numbers that you can take and write as fractions. What kinds of numbers can you take and write as fractions? Bless you. How about whole numbers? Give me an example of a whole number. 2. 2 is a whole number. How do we make it a fraction? 2 over 1. Would you agree? Would whole numbers go in this family? Yeah, you can make it fractions. 2 over 1. I agree. So, give me some more numbers. Go ahead. 4. That's a whole number too. Okay. What about maybe negatives? How about negative 4? Can you make that a fraction? Yes, how? Negative 4 over? Nope, just negative 4 over 1. Negative 4 over 1. Okay, how do you make negative 3 a fraction? Negative 3 over 1. How do you make negative 5 a fraction? Negative 5 over 1. What kind of number is negative 3, negative 4, negative 5? It's not a whole number. Why is it not a whole number? Whole numbers are only positive. Think of whole numbers. Those are the numbers you learn in kindergarten, right? What did you learn in kindergarten? 1, 2, 3, 4, 5. You learn positives, right? If I went to my son Reed and I said, you know, how about negative 1, negative 2? He'd be like, what are you talking about, Mom? Because he doesn't know those yet, okay? He only knows whole numbers, and those are only positive, okay? So what is negative 3, negative 4, negative 5? What do we call those? Starts with an I. Keep going. What are some more I words? How about integers? Okay, integers are positive or negative whole numbers. Does that make sense? Integers can be both positive or negative whole numbers. Okay, so whole numbers can only be positive, but integers can be both positive and negative. Okay, so we got integers, we got whole numbers. What else? We got a lot more bubbles up here. Mixed numbers. How do we make those? We just talked about that today. You make them improper, round the world or round and round and scoot or whatever you want to say. Okay, so mixed numbers, what else? What kinds of decimals? Let's talk about like 0.3. That has a special name. It's called a terminating decimal. Why is it called a terminating decimal? Because it ends and it just has what after it? Zeros. Okay, so how do you make that a fraction? 3 over 10. You look at the place value, right? It's in the tenths place. Okay. How about 0.47? 47 over 100. How about 0.123? 123 over 1,000. Okay, so terminating decimals, they can be made fractions. Again, what makes these all a part of this family? What do they have in common? They can all be made into fractions, okay? How about repeating decimals? 0.33333333 is known as what? No? Does anybody know if it's a fraction? You guys know what 0.3 repeating is as a fraction? There's certain decimals you should know. Like 0.25 we know is 1/4. 0.5 is 1/2. 0.75 is 3/4. 0.3 repeating is 1/3. Thank you. It is a third. It does. And I'm going to tell you. So 0.3 repeating, here's the trick. You still look at the place value, but instead of going over 10, it goes over 1 less than that. So it goes over what? What's 1 less than 10? 9. And when you reduce this, what do you get? 1/3. How about 1 17 repeating. 17, 17, 17, 17, 17. You still look at the place value. What place value? Hundreds, but instead of going over 100, it goes over, one less than that is 99. Okay? Point 1, 2, 3 repeating. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. What place value? Goes over the thousands, so what would we put it over if it's repeating? 999. So repeating decimals can be made fractions too. Okay? So we got terminating decimals. So here you go. We got integers. We talked about those. We've got perfect square roots. We'll get to those in a minute. We got terminating decimals. We got whole numbers. We got percentages. 30% is 30 out of 100. We got mixed numbers. We got repeating decimals. Are there probably more? Probably, but these hit most of them. Okay? And again, here's my thought. Let's go back to my thought on this. Do these numbers actually look alike? Does a percentage look like a terminating decimal? Does a terminating decimal look like a square root? You with me? They don't look alike, but they do have something in common, which pulls them all into the family together. Okay? So let's go over to irrational numbers. You got the definition. It's a non-repeating, non-terminating decimal. What does non-repeating mean? It keeps on saying random numbers. I agree with that. But there's no what? If it's non-repeating, there's no pattern to it. Okay? So remember, if they are repeating, then they have a pattern to it. If they're non-repeating, then they don't have a pattern. Okay? Sorry, I had to keep up with my time. We get out of here at 11:30? Okay, recheck it for me, just to make sure. So, can you tell me, anybody know a number that goes forever and ever and ever, non-repeating? Pi, pi. Okay, so I bet pi is one of them. Okay, pi. Everybody says you forgot the E, Miss Corns. No, it's not the pie you eat. This is pi, pi. Okay, it is. We all know pi to be 3.14, but it's not just 3.14, right? It's 3.1415, yeah, I don't know. We just use 3.14, but we do know that it goes forever and ever and ever. You know, out the hallway, down the road, past Hardee's, up Main Street. You with me? It goes forever, infinitely, circles the globe, you know, a bunch of times, infinitely. So the other place we get them, and we're going to talk about this in a few minutes, is from non-perfect square roots. Notice if they are perfect square roots, they belong over here in rationals family. If they are non-perfect square roots, they belong in irrationals family. Okay? All right, does everybody have this? Miss Handy, can you hand everyone a calculator? All right, so we're going to head to the second page. Does anybody else need one more page, a little more time? Sorry. Well, then we need to move up. Or Nate's got you. Either way, you can move up here. And okay, I'm going to give you a calculator to borrow just for today. And I'm going to show you how to turn it on. So pay attention, and if you're having troubles with it, I'm going to borrow one. Raise your hand, and Miss Handy or I1 can come and help you individually. Okay? So we're first going to talk about perfect squares. And I'm going to go ahead and give you this list. You will see this list numerous amounts of times this semester. Okay, we're going to do an entire bubble on radicals and square roots. okay? And we're going to be talking about perfect squares. So this is just the first time of many, okay? So perfect squares are squares of whole numbers, okay? That's what they are. So 1 squared is 1. 1 is a perfect square. 2 squared is 4. 3 squared is 9. 4 squared, 16. 5 squared, 25. 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 121. 12 squared, 144. Awesome. 13 squared. Awesome. Very good. 169. 14 squared. 196. How can you remember these two? They're just flipped. Okay. 15 squared is 225. I'm going to go up to 20 and stop. 16 squared. 16 times 16 is 256. 17 times 17 is 289. 18 squared is 324. 19 squared is 361. And 20 squared is 400. You need to have these memorized. And in a couple of days, let's set it for Friday. Does that sound good? Gives you all week. I'm going to give you a quiz on having these memorized, because you will not, trust me, you'll want this. You know, on the day of the SOL, how many of you, when you start your SOL, you start, before you even read the first question, you make notes on your paper. And there are certain things that you want to write down. This is one of them, and this is one that you want to have memorized, okay? So I'm going to ask you on Friday, I'm going to say, get out a sheet of paper, and please write the perfect squares for me from 1 to 20. You have 1 minute. Go. Trust me, you only need 30 seconds. I've done this for years and years and years. It's not a big deal. Once you have a memory, you should have all the way to 12 memorized already. How many have all the way to 12 memorized? You should. Okay, so the only ones you got to focus on are these right here. Okay, so by Friday, I'm going to ask you to do this, and it's the only time thing I give you all year long. Everything else, you have as much time as you need within the class block. Okay, but this is the only time thing, because I don't need you to sit there and work it out. I don't need to know that you can go 17 times 17. I need you to have it memorized so that when I say, what's 17 squared, you go, 289. You with me? I need to know that you have that. And it will be for your own good, especially when we get into the radicals bubble. It'll help your math go quicker. Okay, so by Friday, quiz on that. Everybody good with that? Okay, all right, so let's talk about perfect square roots. So if we take the square root is the opposite of squaring. So if I asked for the square root of 16, I want to know what number squared is 16. 4. Tell me, why does this go in Rational's house? Because it's a whole number, and it can be made a fraction, 4 over 1, right? So this is rational. Okay, how about the square root of 100? What times what? What squared is 100? 10. Okay, it's rational, 10 over 1. What if I asked for the square root of 196? What is the square root? What times what is 196? 14. Now that's one of your new ones. Let me show you. Can I show you in your calculator how to find the square root if you don't know it? Okay, so everybody turn the on button on. It's in the bottom left-hand corner. Everybody see the on button? Do you see, if you go up the left side, do you see the x squared button? Now we don't want to use the x squared button, but look above it in blue. Does everybody see the blue, or maybe yellow? Depends on your calculator. Okay, does everybody see the little square root sign above the x squared? Yes? So to get to that, you've got to use the little blue button up here. So you're going to press second. Raise your hand if you're having trouble. Second. Then you're going to press the x squared button. You should see a little square root sign. Does everybody see it? And if you put in 196 and then hit the enter button, what does it give you? 14. If you didn't get it, raise your hand. or ask a neighbor. Does everybody understand what we did? We did second, x squared, 196, enter. Okay? But it does give you 14, and that is rational. Okay? So all of these perfect square roots, okay, these are perfect squares. If you take the square root of a perfect square, it'll give you a whole number, and those are rational. Okay? Let's look at the non-perfect. Give me something other that's on this list. Let's start with maybe the square root of 200. Now, before we put it in our calculator, let's estimate it. Tell me, where does 200 fall on this list? In between what and what? 196 and 225. And we know that this square root of this is 14, square root of this is 15. So what do we know that if it's in between there, what is it going to be? It's going to be a decimal because it's going to be in between 14 and 15. You understand? Let me ask you this. We know that 14 is 14.0, 14.1, 14.2, 14.3, 14.4, 14.5 is halfway, right? Then you have 14.6, 14.7, 14.8, 14.9, and then you have 15, right? So tell me, is 200 closer to 14, 196, or is it closer to 15, 225? So if you had to estimate this decimal, what would you say? 14 point what? 2? Anybody else? Everybody say 14.2? All right, put it in. Put in second square root 200 and hit enter. What do you get? 14.1421. Any more? No. And I may miss one. It's okay. But what I am going to say is, does it end? Is it terminating? No, the calculator just rounds it off. You understand? The calculator just stops it. This sucker right here goes out the door, down the hallway, past Hardee's, up Main Street. You understand? Circles the globe 3 times. It's a non-repeating, non-terminating decimal. Whose family? My family. Red-headed, freckled, and fair-skinned. They will all look alike. It's irrational. Okay, let's look at another one. Let's do the square root of 30. Before we put it in, where's 30 fall? So it's between 5 and, is it closer to 5, closer to 6, or in the middle? Closer to 5, but almost in the middle. This is 5 away, and this one's 6 away, right? So it's almost in the middle. What would you estimate it to be? 5.4, 5.5? Yes, it's closer on the 5 end. So put it in, square root of 30. What do you get? 5.47. Weren't we pretty close with our estimating? 5.47. 7225575. I may have missed one. It's okay. Okay. And everybody says, but it's repeating. It's repeating. It's got 2 7s and 2 2s and 2 5s and a 7 and a 5. Let me ask you this. Could you tell me what comes next? Is it enough of a pattern that you know what comes next? It's not a specific. A repeating decimal will be 1 2 3 1 2 3 1 2 3 1 2 3 1 2, and we know that 3 comes next, right? This you can't really tell. Whose family? Red-headed, freckled, fair-skinned. Don't you think they look alike? They're long, non-repeating, non-terminating decimals. They all look alike. Irrational. Okay. How about this one? Give me a number. Any number. Yeah. Thank you. All right. Where's 128 fall? Between 11 and 12. Closer to 11, closer to 12. 11, so what would you estimate it to be? 11.2, 11.3, put it in. Square root of 128. 11.3. 8.5. Any more? Okay. Again, I may have missed one. It's okay. It's a non-repeating, non-terminating decimal. Whose family? Mine. Everybody agree? If it does not look like this, it's not irrational. It belongs over there in rationals family. Remember, rationals, they look all different. And again, if you can take them and you can make them fractions, they're rational. These guys, can somebody tell me, I'll give you a piece of candy, can somebody tell me why you can't make those fractions? How do we make fractions from decimals? Okay, so why we look at place value, right? So why can't I make this? Because it doesn't what? It doesn't stop at a place value. It keeps going. Does that make sense? I can't, like, every time I try to stop it, it just keeps going. And so if I can't determine a place value, then how can I make it into a fraction? You understand? That's why it can't be made into a fraction. All right, let's do one last one. Square root of, let's do 60. 60 falls between? So 49, 6, 4, 7, and 8. Closer to 7, closer to 8. 8. So if you had to estimate it, what would you say? 7.7. Anybody else? 7.9, 7.8. Put it in. What do we got? 7.7459. I'm missing some. Dot, dot, dot. Okay, close enough. Okay. Any questions? And again, this is irrational. So do you understand the difference between non-perfect square roots? Are all non-perfect square roots going to be irrational? Yes, because they're going to be in between. Okay. And all perfect square roots will give you whole numbers. Okay, which will be rational. Okay. So here's what I'm going to do. I asked you a little bit ago, I said, tell me about 2. And I heard even, and I heard prime, and I heard the absolute value of 2 is 2. So here's what I'm actually looking for. I'm going to give you a bank, and this is the 6 choices that you're going to use, okay? The first thing that you're going to do is you're going to tell me, is it real? Okay, and so here's what I'm going to tell you. All numbers in Algebra 1 are real. Okay, does that mean all numbers are real? I mean every number is real? No, but everything that you're going to learn in this class is real. Once you get into geometry and maybe even into algebra, well, definitely into algebra 2, you're going to talk about some numbers that are not real. Anybody know what those are called? Not real numbers. They're actually called imaginary. Okay, they're actually called imaginary. But again, for my class, every number is real. So what do you know about your answers today? Everything's real. All numbers are real. And again, please don't go to your Algebra 2 class and say, Miss Coy said every number's real. No, I said every number in Algebra 1 is real. Okay? In a couple years, you'll learn about imaginary numbers. Okay? Then you're going to tell me, is it rational or is it irrational? Okay? So how do you know if it's rational? Can be a fraction. Very good. And you can use your little family tree. Okay, but if you can take it and make it a fraction, it's rational. How do you know if it's irrational? It can't be a fraction, I agree. And what do they look like? Okay, non-repeating, non-terminating. If it doesn't terminate, it does not. It doesn't stop. If you terminate something, you stop it. If it's non-terminating, then it goes forever. Now, here's the thing. How many of you look at non-repeating, non-terminating, you may not know what that means? Is it okay for you to put never-ending, never, no pattern? You can put your own words in there. Does that make sense? These are for your notes. Okay, I want these notes to be left out so that when you're looking at a number, you're going down through these choices. Okay? How do you know if a number is whole? Starts with what? What did you learn in kindergarten first? Before 1. 0. Then 1, then 2, then 3, then 4, then 5. Okay? So I want you to think kindergarten with whole numbers, and they're all positive. That's important. All whole numbers are positive. Okay? What do you know about integers? They can be positive or negative. Negative. Spell right. Whole numbers. Okay, so these can be either or. So -3, -2, -1, 0, 1, 2, 3, 4, and so forth. Okay. Some people think that like any negative number, like is -2.3 an integer? No, it's got to be whole. The technical definition is it's a whole number and its opposite. Whole numbers are all the positive ones. The opposites are all the negatives, okay? But it's got to be whole, but it can be either positive nor negative, okay? And the last thing we're going to talk about is a natural number, which I like to call counting numbers, okay? Isaiah, if I asked you to count the students in the class out loud, can you do that for me? Start over there. Ready? Go. Good. What did he start with? 1. So these are numbers you count by. And everybody says, Miss Corns, aren't those just whole numbers? What's the difference? What's the difference? It didn't start with 0, okay? So 0 is a whole number, but 0 is not a natural number. Okay, natural numbers are the ones you count by. Okay, so just imagine counting. If you can count to it, then it is a natural number. Okay, and those are the, I know there's a lot more. You can tell me even, odd, prime, composite. You know, I'm not worried about that today. Here's what I'm worried about today. Okay? Any questions on that? Okay. Is it 11:30? Okay. Why don't you grab Nate's? That way you don't have to stress. He doesn't mind at all, right, Nate? Okay, let's just look at a couple examples and see what we can do. All right, let's start with example 1. And let me ask you a question really quickly before we begin this. Is it possible to have a number that is both rational and irrational? Why not? Well, either it can be made, say it a little bit more technical. Either it can be made into a, or you can't. So here's what I say. My nephew Wesley, he can come over to my house and play, but at the end of the day, who does he belong to? He belongs to his mom. Does that make sense? He belongs in that household. Okay? My boys love to go to Aunt Sarah's and play, but in the end of the day, they're mine and they belong to me. Okay? They belong in my household. So you can't belong to two households. Okay? Either it can be made a fraction or it can't. Okay? All right, so let's look at 23. Let's start at the top. Is it real? Yes. Why? Because all numbers in Algebra 1 are real. Okay? Whose house? Rational or irrational? Rational, because we can take 23 and make it a fraction. Okay? So if it's rational, then it's obviously not irrational, right? Okay? Is it whole? Yes, it is whole. Is it an integer? Yes, integers can be positive or negative whole numbers, right? Is it a natural number? You think if Isaiah counted long enough, he'd get to 23? Yep, I do think. So this answer, or this question had 5 answers. Okay, let's look at the next one. -5. Is it real? Yes. Whose house? Rational, because it can be made a fraction. Negative 5 over 1. Is it whole? Why not? Because it's negative. Remember wholes? My son Reed, you ask him about negative 5, he ain't going to have a clue as to what you're talking about. Okay? Kindergartners don't know negatives yet. Okay? Wholes are only positive. Is it an integer? Yeah. It is an integer. Remember, integers can be either positive or negative. Do you count to negative 5? 1, 2, 3, 4, 5, 6, 7, 8, negative 5. No. Okay, so this one only had 3. Okay. How about 2/5? Is it real? Yes. Whose house? It is rational because this is a fraction, right? It's not, you can't write, can it be written? It already is. So it's definitely rational. It's not irrational. Okay. Is it whole? Integer? No. Count to 2/5? So this one only had 2 answers. How about 0? Is it real? Yes. Rational or irrational? Is it, my question, what did the red-headed freckled numbers look like? They're long, big decimals. And I said, if it's not one of them, it better go over here. I know you think you can't make it a fraction, but you could over 1. 0 divided by 1 is 0. So it is rational. Okay? Is it whole? It is whole. You do include, is it an integer? Yes. And everybody says, but it's neither positive nor negative. But it is included in the wholes, which means all wholes are integers as well. Okay? Do you count by 0? Is it natural? No, we don't start with 0. All right, so my last question for today, and we're going to stop for here for today, is can you have an answer with all 6 choices? Yay or nay, and why? Is it Gracie? Right. So it could have 5. So it can't be both rational and irrational. Very good. I owe you a piece of candy. Okay. Can you have one that only has 1? And why? Here, Landon. Very good. It is real. Remember, it's part of Grandma Real's family. And from there, it has to go in either rational or irrational. So it'll have at least 2. Okay, so I'm finished for today. You lucked out. No homework. I'll have to finish this tomorrow. Very good.